Hello, everyone. I am Amin Jafarimoghaddam, and I am working on aircraft control and navigation, supervised by Professor Manuel Soler. And my PhD is about commercial aircraft trajectory optimization using advanced mathematical and computational optimal control. So let's get started. In this presentation, I'm going to talk about motivation and problem statement, optimization methods, and the methods that we have already proposed. One of them is called perturbed analytic direct transcription for optimal control, or PADUC. And after that, I'm going to talk about the building blocks of PADUC, which are segmented Adamian decomposition method and a technique called average nonlinear programming. And then we compare the results of PADUC with other transcription methods from different disciplines. And then we briefly discuss another method called the indirect bank singular algorithm, or called IPSA. And then we talk about the potential future works. Okay, here I'm going to explain how commercial aircraft trajectory optimization can be put into a formal and standard optimal control problem. So here we have an objective function. Do I have a pointer here? Yeah. Here we have an objective function, and this objective function can be a combination of arrival time, fuel burn, and with contrail regions, contrail avoidance region, and which is subjected to some constraints, dynamic constraints, that here we have a dynamical equation, and all the variables here are in vector space. So we've got a boundary condition, initial and terminal condition, together with an inequality constraint, which applies to both state space and control space. So it is like if we consider the states as positions, which can be longitude, latitude, and altitude, together with velocity and mass, we're going to move this initial state to a final given state, which also satisfies these constraints, these dynamic constraints, and the controls that are responsible to take action in time are throttle setting, heading angle, and aerodynamic path angle. And this is a simple formulation of this optimal control problem, but still it is general. So here, for this nonlinear function f, this includes many terms that can include many complex terms related to wind fields, which can contain uncertain parameters. And it also includes the drag force and the engine type and any other information related to the aircraft model. So in general, this optimal control problem is can be a stochastic optimal control problem in a Markov sense. So this is considered as a very complex optimal control problem. And unfortunately, there is a lack of mathematical breakthroughs and understanding with respect to this complex optimal control problem, which is the main reason that motivates the present thesis. Okay. As for the optimization methods, we have different methods here: dynamic programming, indirect Pointryagin method, Pointryagin maximum principle, direct transcription method, also known as numerical method, Minimax method, which is based on the principle of game theory to some respect, and meta-heuristic methods such as genetic algorithm, particle swarm algorithm, and simulated annealing, so forth, and learning-based methods that use the architecture of a neural network to optimize a given objective function in a parametric form. So for the dynamic programming, and the first three methods that I've highlighted here, the first is dynamic programming, and unfortunately here we have a problem called curse of dimensionality, and this is something that restricts application of this dynamic programming method, although the method is very complete and it uses the Bellman principle of optimality, but for this reason, the curse of dimensionality, this method cannot be applied to many practical situations. So this leaves us with two methods here: indirect Pointryagin maximum principle, which is the analytic method, and the other one, which is called a numerical method. So the drawbacks with the direct numerical method, I can just list them as a chance of falling into local optima. So this is somewhat, what I think of is that the method is somewhat generous because it's not going to reject our empty hands. And always we're going to solve a problem with this method. We can end up with some solutions. So even if the problem is complex, we have some parameters to tune. We can use different methods like homotopy deformation methods, proximal methods, and control parameterization techniques, what have you, to make the method work. So, but again, this is a drawback of the method because we're not looking for local optima and we're actually more interested in finding the global optima. So it also has limited accuracy, especially for singular problems, high computational time for large problems, and sensitivity to the initial guess. So the drawbacks of the indirect method can be counted as lack of theory for problems with state inequality constraints. And in fact, the Pointryagin maximum principle has not yet been proved for an optimal control problem with state inequality constraints, at least not that I am aware of. So then we have complexity with respect to the singular problems, complexity in computing co-state variables, and lack of theory to identify the number of possible discontinuities, which more or less refers to the singular control problems. So for all these reasons, the indirect method is not a robust method. So the thesis follows in designing a new direct transcription method to work around the drawbacks of the direct numerical method that I have listed above, and to seek for the answer of the question, is it possible to design a robust indirect algorithm? So, just to mention the story behind transcription methods, here I will be talking about perturbed analytic direct transcription method, or PADUC, something that we have designed. And this is a new direct transcription method, which is based on two elements. One of them is called SADM, which is by itself a new method, a new differential solver. And the other is average nonlinear programming, or ANLP. So sourcing the issues with direct numerical methods, we can say that first we need to consider that the direct numerical method is based on transcription methods and parameter optimization modules. So the parameter optimization module is something that we are not trying to modify in this thesis, but the direct transcription method is the subject. The transcription method is the subject that we're going to make it better by SADM, which is a new method that we have designed. So we consider again the optimal control problem here. So for this optimal control problem, we form an augmented cos, or Lagrangian, which is something in this form. And this is the responsibility of a transcription method. So when we have this augmented cost, we can solve the resulting KKT system by an optimization module, which can be interior point methods, sequential quadratic programming, and so on. So this term here is the main focus of a transcription method. So this is called state deficiency function, which is a difference between the estimated state and an adjustable decision variable. So this estimation comes from different numerical solvers, such as Euler method, Runge-Kutta methods, Adams-Bashforth, and so on. And the story behind that goes back to the time of discovery of this expansion. So this Taylor expansion, that we can use it in Jacobian composition forms, we already have this f of x0, which is related to the Euler transcription method. But for the successive Jacobian composition terms, we don't have an explicit for. So if we try them in the exact Jacobian form, we end up with a very, very long symbolic term that we cannot incorporate it into an optimization module. So if, in fact, we approximate this term, the numerical solver is called the numerical method, or the transcription method is called the numerical method. And if we compute them directly with a recursion scheme or anything that make it work and to make it easier to compute, we can call it segmented Adomian decomposition method, which is the new method that we have designed here. And if these terms remain unknown and we're not going to deal with them and simply take them as decision variables, it is called the collocation methods. So this is.
You have already consumed 10 minutes.
Oh my God. Okay. Okay. This is the segmented Adomian decomposition method and how it works. And actually here we use a linear operator here and the inverse of a linear operator to form this. And in an example, we can see that it works like this, and it computes all the terms in the recursion scheme. So the question is, segmented Adomian decomposition method is a recursion scheme to compute Taylor terms? In general, no. Because in general, Taylor expansion can be considered as a special case of Adomian decomposition method. So the average nonlinear programming is a technique that uses with a low-dimensional minimizer and connects it to a high-dimensional minimizer. So if we consider the problem P1 as a low-dimensional minimizer and the problem P2 as a high-dimensional minimizer, the link between them and the formulation of this low-dimensional minimizer is something that we call average nonlinear programming. So the closer the costs, the closer the corresponding multipliers. So in an algorithmic form, we consider just one control over a group of segments, a group of discrete segments that we solve the dynamics over these discrete segments to make sure of the stability of the solver. But we only have a few minimizers, a few decision variables. And here, this is a switching point version of average nonlinear programming. And this is some results of solving a 3D free routing flights with PODUC compared to average nonlinear programming. And in fact, we're using average nonlinear programming as a rough estimation of the optimality. So, but we already can note here that the average nonlinear programming is already close to the optimal solution and can beautifully detect the structure of the optimality. So here is a comparison of PODUC with other transcription methods. And here we have a bunch of transcription methods, a trapezoidal, Hermite-Simpson with fixed middle point and relaxed midpoint, Gauss-Lobato, fourth order, fifth order, and different orders of Runge-Kutta methods, and also different orders of PODUC. And here, the failure, and here is the specification of the problem that we have solved. And the problem is for a Madrid Paris free routing flight, and with real Wien data, BODA3 model, and uniformly distributed grid points, and the other fixed parameters to compare these transcription methods. And we see here that if the transcription methods, in fact, can be compared with respect to different features, but this is only one feature that we're showing here, which is called the stability of the solver. And here we see that the failure in the collocation methods are higher than the other methods, and specifically we see that the PODUC performs better than the other transcription methods in terms of stability. And the other comparison is about an aircraft problem in a climb phase. And here we show the performance of the computational time, and the lowest part here, the lowest graph here is reflecting the solutions of fifth order PODUC, which is the lowest PODUC form that we have used, but it still performs better than other collocation methods in terms of computational time. So something that we have note here is that the fourth order approximation is inconsistent with aircraft dynamics, and this is something that has something to do with Lipschitz continuity of the system. And the other comparison criteria shows that the PODUC is performing better than the other transcription methods. So Here is a scheme of the IPSA algorithm that we have developed.
You need to finish.
Okay,
Just conclude, please.
it's okay.
Maybe you can skip this.
That will be
It's
conclusion.
interesting. I'm sorry, but
Okay.
uh,
And here is some insights of the future works. And the results from PADOC and IPSA are promising enough to think of developing some libraries based on these methods. That's it. Thank you.